Hello, everyone. My name is Mr. Bice with Susquehanna Valley High School here in Concord, New York, and there's my email address if you want to contact me. Right now, we're doing Unit 12, Lesson 4, Conditional Probability. Name of the class is Algebra Common Core, Algebra 2 Common Core, and this is the non-Regents version. If you don't understand what I'm saying, you can look at that QR code, just scan it, and the guy who made these worksheets is going to talk to you. However, he doesn't have that diagram. That is a conditional diagram for a computer program, or at least part of a computer program. What is conditional probability? When the probability of one event occurring changes depending on the other event occurring, we say that's a conditional probability. The language and symbolism of conditional probabilities can be a bit confusing from time to time, but the idea is fairly straightforward. So if we can understand the symbols and the language, as long as we got that down, the idea is straightforward. We can develop using a two-way frequency chart, which we used in the last lesson here. Same one. Okay, so let the following letters stand for the following events. There's the key. Now, if a person was picked at random, find the probability the person was a female. Female. How many females are there? There are 22 females. Probability it's female. Out of all, everyone was 52. So it's 22 out of 52. If a person was picked at random, what's the probability the person was going to college? How many people are there total? Total, 52. How many are college? College, 29. Okay, those were the straightforward ones. How many are female? 22. How many are going to college? 29. Okay, now, going to college, given that they are female. And the way that we draw that is, or the way that we write that is, the probability you're going to college when you're female. Going to college, given they're female. Draw a Venn diagram below to help you justify the ratio. Okay, I hope you didn't write this down yet because things are going to move. It's going to help you justify the ratio. Now let's think for a second. Our population. Another way to say population is our sample space. Our population. Our sample space. What is that? It is females. So ignore all the guys. Ignore the guys. Notice inside my Venn diagram, I only have girls there. Okay? So draw a Venn diagram to help you think about this. Now, how many females do we have? We have 22 females. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. We have 22 females, and they are inside the female circle. Now, I'm going to tell everyone going to college, go into this little space here. Everyone going to college, if you're a girl, you have to stay inside the girl circle. If you're going to college, you have to be inside the college circle. Okay, girls. Let's get into that space. Suck in your guts. Squeeze. There we go. How many went in there? 13. How many are not? 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, good. Now, going to college, given that they're female, I only care about females, so that's all I put on the Venn diagram. Draw a Venn diagram to help you justify the ratio. What do I have total? I have total of 22. Total, 22. How many are going? Probability they're going to college. 13 are standing inside that college spot. That's the and. How many of them are female and going to college? That's conditional probability. You have to have two conditions. You're female and you're going to college. Which is more likely? A person picked at random will be going to college, given they're male, for example, probability college / male, or the person will be male, they're going to college. Show the calculations for both. Do you notice? This is my whole population. Which is more likely? The person picked at random will be going to college given they're male. So I'm only going to look at males. How many males are there? We have 30 men in our population. How many of them are going to college? 16. 30 males, 16 are going to college. Do you see something here? Male, 30, going to college. I'm going to get rid of that 30 in a second. Let me go back down. The condition here is that you're going to college. So, or the person male are going to college. Okay, so here. That's the condition, given that they're going to college. So we're only going to look at the people going to college, and we're going to find out if they're male. So we're only going to look at the people going to college, 29 of them, 16 of them are male. Given that they're going to college, 29 of them are going to college, how many of them are male that are going to college? What I wanted you to see here was the fact that that is the denominator, the C is the denominator, the M is the numerator. Okay, so even though they're different numbers. Now, which one is more likely? Well, this is more likely. I can turn it into a decimal. You should know that it's more likely since the numerators are the same. Let's turn the page. Remember to ask a question if you're confused. You can generalize this process to calculate conditional probabilities based on counts, and a way to calculate these probabilities based on other probabilities. So I'm going to have other fractions, and I can find out the new fraction. I can have other percents and find out the new percents. In these generic Venn diagrams shown to the right, each dot represents an equally likely outcome in the sample space. Some of these fall into event A, some only into event B, and some in both, some in neither. What? Yeah, neither. Let me see. Do I want steak? Do I want fish? Do I want vegetables? Let me see. Okay, well, no, this is what I'm eating. Sorry. So steak, fish. This is steak and fish. Surf and turf. This is neither. I'm having a pasta dish. Okay, consider the probability of A occurring given that B has occurred. Stop. Given that B has occurred. Stop. Since B has occurred, we're only looking at those dots. I don't care about any of this over here. Since B has occurred, only look inside the B circle. Consider the probability of A occurring given B has occurred. Give a formula for the probability based on counting the number of elements in each set and their intersection. Let's think about what's on the denominator first. I have to count all of the dots inside B, because that's all we're concerned about. Given that B occurred, I have to count all the dots inside B. How do you do that? The number of B's. This is what I want. Top is what I want. I want this part in here. So I have to count. And what did we call that part? We called that part the intersection of A and B. Remember, the N means count it. This is an N. I'll put a little tail on it. This is an upside down U. It means intersection. There. I wrote a formula based on counting the number of elements in each set. Well, that's very straightforward. It says N of A intersect B divided by the number of things in the whole sample space, the whole number of elements in the sample space, all over the number of things in B divided by the number of things in the sample space. Now, we're just going to rewrite this because this is a definition. Okay, this means the probability of A intersecting B, or A and B. Divided by the probability of just B. That's pretty handy. It's great when we can count elements that lie in events and their intersections, but a lot of times we can't. For example, take a look at this one from the previous homework problem. A survey was taken to examine the relationship between hair color and eye color, and the chart below shows the proportion of people we surveyed who fell into each category. If a person was picked at random, find each of the following conditional probabilities. Show the calculations you used. Find the probability the person picked had brown eyes, given that they had blonde hair. Okay, what's going to be the bottom of the fraction? Bottom of the fraction is going to be how many people had blonde hair. 0.35. Also known as 3500ths. How many had brown eyes? 1000ths. The condition is, I'm not looking at this. No, I'm not looking at this. I'm looking at that, because the condition is you have to be blonde already. You have to be blonde already. Now we're looking for how many of them have brown eyes. You can do that, and we can either leave it like that or round. .29. Find the probably person had red hair, given that they had green eyes. Given green eyes. We're looking this way. Red hair. So that means if you are only looking at green-eyed people, 60% of them, green-eyed people, have red hair in this population. Does having red hair seem to have some dependence on green eyes? I'd say so. How can you tell or quantify this dependence? Well, the fact that we just did the arithmetic there, it's like 60% of green-eyed people in the sample had red hair. Does having red hair seem to have some dependence? Yes, red hair depended on if you're green-eyed. Wow, that's something. Okay, this seemed to be a fast lesson. Ladies and gentlemen, I expect questions. Come to me with questions. We'll help you out. Sort it out. Have a great night. I'll probably see you. I'll probably see you tomorrow. Bye. Oh, do the next 2 pages for homework. Of course. Of course you got to do the next 2 pages for homework. That has a probability of 1. It's always given. Ciao.